I guess we're starting now. So yeah, again, thank you for coming tonight. I'm David. You may have met me if you've been to any of the events of the Cambridge University AI Society, CUAI. We are hosting the machine learning workshop together with Hackbridge, in particular, over here. And to more generally be part of the Technical Societies Coalition, which is the big group of societies. So, can you use that?
Yeah, sure. So I'm from Hackbridge, so we're a technical entrepreneurship society. So we're collaborating with CUAI in this instance to give you guys an opportunity to learn a little bit more about machine learning, prepare for some of the upcoming Mythos-led projects that we're running this year. So hopefully this will give you an introduction to that, and we really hope you find it interesting and fun. And Technical Societies Coalition is just a group of all of the technical societies in Cambridge. So we try and kind of foster collaboration, work on these kind of multidisciplinary projects. And so this is our sort of first intro project series with the TSC up and running. So I really hope that you enjoy it, and thank you very much for actually coming today to this in-person session, which has been a long time coming. So yeah.
Thank you for the Okay, so as we said, today we'll be introducing machine learning. And now, just to warn you, or more like relieve you, this is not a mathematical, hardcore, we're going to do algebra, algorithms and all that. This is more of a general introduction. We do have some equations. That's why I'd like to ask how many of you are actually engineers? Just out of curiosity, it's 50%. And people in the chat can also type in if you want. And how many of you are still like science or maths or that related, but not an engineer? And then the remaining, how many of you are like completely like philosophers or historians? Okay, cool. So we've got a good mix today. Well, let's get into it. So. Let's see if this works. Okay, the pointer isn't working, so let's click here. Cool. So, what is machine learning? Now, very simply put, it's just a bunch. So we have computers, and then we can run these things called algorithms, which are just automated processes on the computer. And in particular, if you know your Coxswain friends, they're always busy programming, right? And they have to write a particular algorithm to do something. So machine learning comes in here, is that you're actually writing an algorithm that then tries to learn itself what to do, which is kind of pretty different if you think about it. So it will, in particular, it can learn from experience. So if you ask it to do something like recognizing cats versus dogs, as you may have seen, just by observing the data, or experiencing the data, it can learn how to do it. And essentially, they improve automatically through experience. And in particular, for the people here who have done statistics before, actually machine learning, which is this huge term that's being overused nowadays, it intersects very much with statistics. And essentially, you know, if I have this data, how do I learn things about it, which is very related. Basically, how do I infer knowledge from data? That's essentially all you need to take away. That's machine learning. Now, machine learning is kind of part of this field called artificial intelligence, which is, as you know, artificial intelligence, right? So we are building intelligence. Now, what is intelligence? We'll come back later to that. Machine learning it's been around for a long time, and it's actually only recently, right? I think a lot of you have heard of all these recent developments, but only recently has it come along, and it contrasts itself a lot with symbolic AI, which is what people maybe 30 or 40 years ago may have done, but you may know about it. That is basically what computer scientists used to do. They program a set of rules, like this is a dog because it has like 2 ears or a nose or whatever. And this is a cat, it's particularly different. And then you just write these rules in, and then you hope it does something, and it turns out it really just sucks. That's why it was really, like automatic picture recognition was not really a thing until 2012 with the deep learning coming up, which we'll talk about today. And then loosely related to artificial intelligence, we have biological intelligence, which is, well, we all have a brain here, right? So that's kind of what biological intelligence does. We try to study the brain and intelligence as it can come in nature, which is actually different from AI, but the two are still sort of linked, like cousins. And then to come back at what intelligence is, well, sorry to disappoint, but actually no one has agreed yet on what intelligence is. So even the experts, they will all give you different answers and they like to fight about it. So I'll just leave it there. Intelligence is essentially whatever you think it is. I'm sure you all have some intuition. Yeah, that's pretty much the big picture. So machine learning is this part of AI that tries to come up with algorithms that can learn from data. And now this is maybe young guns, so people who looked at machine learning more. Is one of the original people pushed deep learning essentially. So there are different kinds of, within machine learning, there are different kinds of tasks. In the middle, we see supervised learning, which is what we all know. Let's say I have a dog and a cat, and I literally tell the computer, okay, this picture is a dog or this picture is a cat. And then I will make it go through like millions of such pictures, given that you tell the computer what is the right answer. So that's supervised learning, and it allows you to learn to teach the computer essentially how to recognize animals or planes or faces. But you need some human to actually label this, which is kind of crazy to think about. It's like a lot of pictures to label, so have fun. But people have done it. People have also started looking at unsupervised learning, so the bottom, which is where you do not have the labels. So whatever I just told you still holds, but I don't tell the computer what is what, and it just figures out by itself. Kind of sounds like magic, and it's still being developed, so it's not super practical yet. And then the cherry and the cake. I will explain a bit why the cake, but the cherry is reinforcement learning. And reinforcement learning essentially boils down to having an algorithm literally play a game, for instance, like AlphaGo. You may have heard of DeepMind. Essentially, the idea there is that you make an algorithm that essentially learns how to play or how to collect as much reward as possible in a given game. Or you guys, in real life, as students, try to collect as many tripod points, right? So you're actually solving a big reinforcement problem right now. This is exactly what reinforcement learning is trying to do, but instead of you guys, like humans, sheets that try to do this. Yeah, if you follow DeepMind, you know that's there. Now the cake is basically his opinion, right? So he thinks unsupervised learning is the main thing. I think you guys can agree. If you have an algorithm that learns itself to decide whether there's the concept of a cat and a dog in the first place, and then it learns how to distinguish between them. That's like that is a whole different level. So interestingly, he puts reinforcement learning on top because he thinks that's very niche. It's just for games, but people have different opinions on this. So that was pretty much it for machine learning. You know pretty much what we're trying to do. How does this work, right? So unfortunately, we need a little bit of that. Essentially, this term called loss functions. So in the machine learning model, essentially what you have this algorithm, right? And you can tune it. So you can tune it to be more sensitive to say, I think it's a dog because it has ears or because it has a nose, and you can tune how much it cares about each part and what it cares about. Essentially a bunch of free parameters. And you have to essentially tune these knobs such that this algorithm gives you the correct answer. And if you do this manually, you look back at ground zero, symbolic AI, you have to do this as a human. There's no way you can do this. And this is why machine learning has not really caught on in a long time. So how do we do it nowadays? We try to essentially define a loss function, which defines how well does this algorithm do, right? So how, for instance, with the cats and dogs, how many times does it guess the wrong animal, right? And then you try to basically minimize it. That's it. It's that simple. You try to reduce the number of mistakes or increase the number of right guesses. And this is called a loss function. So it's a function that depends on the data, which usually people write y, and a bunch of parameters p. Yeah. And in addition to that, you pick what kind of model you want. So bear with me if this seems a bit abstract for some people. You'll see examples very soon. So this is it. This is machine learning. It's just this thing, minimize this loss function, and then once you've minimized it, you have your parameters, right? You know how to tune it, and then you use it in the real world, and you get things like Facebook recognizing the faces, which is a little bit uncomfortable sometimes, but this is essentially how it's done. So still a bit abstract. Now let's give an example. So the simplest example is linear regression, and people may have used it before. It's literally, you have this loss called the mean squared error. I'm not going to go too much into it. If you know about it, you probably already know how to use this. And essentially what it is, if you on the y-axis go with data, which is a bunch of points, linear regression asks itself, what's the best straight line that goes to it? This is in fact statistics. As I said, machine learning is very, very much intersecting statistics. Right, as a student, you probably can draw a line through it by hand, but as a machine, you actually have to compute some things. And what you end up doing is you have this linear model, which just describes I can draw a straight line from x against y, and then I plot it against the input x, which is on the x-axis, and y. And then we have the parameters m, which is like how much is the slope, how steep is it, and c, which is how high or how low. And these form your parameters. So now the loss function is just written there. Don't worry about it. It's a bit abstract, but essentially you try to minimize the error. So you want the straight line to fit as well as possible. It must look as pretty as possible. And that's it. So you minimize the loss function and you draw the y-mesh slope. An example of unsupervised learning, which is slightly different, just to give you an example where it's used. Imagine you have a bunch of points and you just want to say, these points, which cluster does it belong to? Because, so I'll show you an example here. Essentially, if you look at this picture, you have these black dots and it looks like noise, right? It looks like a mess. So now you can ask yourself, okay, is there any structure in here? Yes or no? I mean, as a human, you look at this, you probably say no. It looks kind of like noise. But if you run this algorithm on it, it will actually find 3 different groups that are depicted here. And this is called clustering. And it's unsupervised because you did not tell which point belongs to which cluster, right? So even though this seems very simple, if you think about it, if each of these dots is like an image of a face, and now you ask this algorithm to cluster this, it will automatically find groups. And if you do that, it turns out clusters all separate between genders and ethnic groups actually, completely in its own. So what I'm showing you here is basically the simplified version, and it's called unsupervised learning, where you do not have to provide that much information at all, just the data. So, and finally, reinforcement learning that I discussed. I'll give you a very simple example that hopefully you guys are going to do. So gambling, right? Putting in your money. There's a particular game you can play where you just have a coin flip, and at every flip, there's a probability that it lands on heads. The moment it lands on heads, you double the money. So that's pretty nice. But the moment it lands the other way, you lose everything you just put in. So now the question, if you start with £1 and you're only allowed to put in like, whole pounds, because we're playing with pound coins, what would you do to get the most money? This is an example of a game that you're playing, and it's reinforcement learning. This is, if you ask a human to do it, like if I ask one of you to do it, maybe you'll lose the money like after 2 or 3 rounds, right? But maybe the machine can do better. So over here, our loss function that we try to minimize is essentially the negative of the total expected reward, or in other ways. We're trying to maximize the amount of money we're going to earn when we run this algorithm. Yeah, so we're not going to rewrite this guy, but instead, it turns out if you run reinforcement learning algorithms, this algorithm finds for you the best tactic. And it turns out, this may look very funny, it looks like a bunch of pyramids with some peaks. And what this algorithm is telling you is that if you have, for instance, 25 pounds, you should go all in. But if you have 24, you should be putting in 1 pound. Apparently, that's the most optimal algorithm. Unfortunately, to understand this more, you need to move more to the maths. And there's some very interesting maths behind this. If you ever take machine learning next year in engineering or something, you may learn about this. But yeah, this is an example of reinforcement learning. Pretty cool. And you can obviously imagine, you know, if you do gaming, if you play a game, you can do something similar. It finds the best way to play a game, or the best way to invest your money in the stock market. People are trying to do this. So yeah, how do we actually do this optimization? Because everything I just told you relies on optimization. So in the simplest cases, you can just use math to solve the parameters. But in the most general case, as long as the loss function is smooth enough, you can do something called gradient descent. So it looks like this. You have your data, and you have some loss function, which is a function of the parameters. So this two-dimensional grid is essentially the grid of parameters. And you're trying to search which set of parameters is the best. And if it's smooth enough, you can just imagine you're holding the ball off the hill. So you start over there at the top, and you just make it roll down along essentially gravity. It's called gradient descent because there's gravity, but because we make it go down along the steepest direction, or roughly the steepest direction. And if you're lucky, you end up there. And if you're lucky, again, that what we call minimum is a good set of parameters that you do very well. If not, then you have to find another one. So this is essentially what modern machine learning, a lot of it is all about. This is just an extra slide, depending on how many. So this is just slightly more mathematical in the sense that everything if you zoom out, it's fine. So I'll just go through this. It's not too heavy. So we've now finished essentially machine learning. We know what it is, very roughly. But if you actually take machine learning next year, or if you know more about it, a lot of people talk about probabilities. So what I just showed you, nothing of that had to do with probability, right? I was talking about minimizing some function, but a lot of people talk about maximizing some probability. So it turns out that if you take your loss function, and you know, your loss function, it can essentially be interpreted as the negative logarithm of a probability density. This is too abstract, don't worry about it. And once you have a probability, you can use Bayes' theorem. And then with Bayes' theorem, you can actually infer not just which parameters are good, but you have all distribution of the parameters. And what this means is that you can estimate how certain you are about each parameter. So if we go back to linear regression, I can find the best slope, but I don't know how accurate I am. And if you take this perspective, long story short, you can actually quantify how accurate and how reliable your estimate is. So I hope that makes sense. It's not too important because you already know machine learning is. This is just extra. And then the final question before we go to some examples, is it just curve fitting, right? Like it really sounds like we're just fitting in curves. They don't have to be straight lines, they can be curved, or they can be like two-dimensional or three-dimensional. The answer is kind of yes. I mean, if you think about it, even if you try to recognize a bunch of faces, you are essentially drawing a huge kind of function through this high-dimensional space, which contains all possible faces. And you're trying to sort of regress against it and find a function that fits data the best, and then you can start predicting and interpolating between faces. But this doesn't say anything about causation. So again, for the people here who are studying more for machine learning, we're essentially just describing the relation between X and Y. We're not saying X is causing Y. So if you go to medicine, people often want to know what is the cause of this disease. And if you try to apply any of this machine learning, you'll find quickly that you cannot actually directly say anything. You need to do more. And this is called causal machine learning, where you try to actually infer, did this actually cause? If I get this disease, was it because I was smoking, or was it because it was raining and it was cold? You cannot really do that with the tools that I've just shown you before. Just so you know, machine learning is definitely limited in what it can do. And this is kind of like the edge of research if people are doing this right now. So that was machine learning. Hope you all enjoyed that. Of course, the buzzword that we'll go through in the next 5 to 10 minutes, and probably why people came here, is because of deep learning, right? Deep learning, like Facebook, Google, all these big companies are throwing in this term. And essentially, it's not the same as machine learning. So if we actually go, what is deep learning? In short, it's a special case of machine learning. So machine learning is super broad, it's been around for a while, as I said. Deep learning is actually a really, really small subset of machine learning, where the trick is to essentially use a component and stack them on top of each other like 100 times, and then run the whole thing. That's what they call deep learning. And we'll show you example of most common algorithms that they use. It's only possible recently because if you stack like 100 of these algorithms on top of each other, you need a lot more computers, right? Because of these things called GPUs, which are essentially processors for games. People only recently managed to actually run these things, train them, and get incredible results that we'll see at the end of this presentation. Now, the most famous example is a deep neural network. And many libraries, so if you want to actually use these things, there are existing libraries like in Python that allow you to just use these off the shelf. And tomorrow, if we come to the coding part of this workshop, we'll show you how to use them in the library for PyTorch. So you can actually start to classify some images yourself. So the neural net started, well, sort of with neuroscience, sort of like a biological neuron. And I would say, loosely inspired, because it's quite different. But in case you don't know how the brain works, your brain consists of cells, a lot of different cells, but one of them, the most important probably, is the neuron. It looks like this. Essentially, all it does is that you get inputs, and then these inputs are like connected, and then if the inputs are enough, it will actually send a signal to this arm called the axon. And then the axon connects to other neurons, and you have this network of neurons, hence a neural network, right? So you get some inputs, and these action potentials, or the signals, that's what they call it, go through it. And then you get neurotransmitters, which gives you essentially the signal to other neurons. I just put these terms in, but if you don't do neuroscience work, just the idea that it integrates signals and sends signals through. That's all you need to know. So now what people do in deep learning is they try to copy biology. So what are we doing? Okay, if I have input X, just like my inputs, I have just a bunch of these variables, and I feed them all together by multiplying them by some weights. So each X gets multiplied by a scalar number, for instance 1 or 2, which means that I actually get double the input in that one, or maybe 0. I don't care at all about that X. So just multiply it by double, and then add them all together. The 1 and the b, by the way, is just an offset. So you'll eventually see it in the equation if you want to know the equation. So now we're going to the neuron. We put it through some function, which basically is essentially just a function that becomes very high if my input is high, becomes low when my input is low. That's essentially what it does. It just tries to map your input to the output. There you go. That's the neuron that we're going to use. Pretty simple. This is essentially the equation if you want to write it down. And tomorrow we'll look into this, in real life, what this actually does, how it works. This is essentially all there is to the neuron. And pretty much almost completed deep learning. You think it looks like this? It's roughly a match, right? Roughly. I mean, of course, in real life, the actual neuron is so complicated, but we don't worry about that. We're almost complete. We have these neurons. Now all we need to do is just stitch them together. So, and when we stitch them together, in particular, we can define layers. So you see that in the picture, where each layer is connected to the next layer. And by stacking these layers, each layer contains, let's say, 10 neurons, 100, I don't know. And then you stack these layers together, you get 500, 1,000 neurons, 10,000 neurons. So this is where the numbers get really big. And you start to get into the deep learning machine. And exactly, you go shallow to deep. In particular, it kind of looks like this. So we have some inputs that are blue, that's X. And they are fed in, as I just showed you before, for each neuron, now for like a bunch of neurons, we call hidden layers in the sense that they're in the middle. And then essentially repeat this, so it didn't draw, you repeat this until we reach out. So that's your neural net. Notice that everything is flowing from left to right in this picture. And now, how do we do optimization? So I'm going back to it. How do we pick the weights? So I just showed you the weights and the biases. How do we pick them? Again, we have a loss function to optimize it. And in particular, I'm not going to go into the details, but there's an algorithm called backpropagation, which allows you to efficiently go down this hill that I just showed you a few slides before. And hopefully, you end up in a place where it's nice and your neural network works. But because of backpropagation, we managed to do this. So in 2012 or around then, it was one of the first times people successfully applied this and got some results that basically destroyed all the symbolic AI that came before. So that was kind of like the start of the revolution of deep learning. Yeah, so there are different algorithms that do this, but essentially the idea is the same. You just go down the hill. Now, for tomorrow, so this is slightly more detailed, but when we have a neural net and we give it some data, it turns out the amount of data we need to actually make this neural net work is huge. So you easily go into 100,000 or even millions of images, right? So how are we supposed to fit all of this into the machine? It's not going to happen. Too bad. Well, people have made it work by basically splitting this data set into groups called batches. So this is called mini batching. It's essentially a very small detail, but it's very important because it allows you to essentially feed everything in and to learn it step by step. And then you have to supply a certain learning rate, meaning how fast do I want to optimize this. Yeah, I feel like this could be a bit too much detail. Essentially, you keep repeating this until you reach the epoch. This is an example. So after you train for each epoch, you essentially test. So you trained the network, and they actually test the network to see how well is it doing on data that I've never seen before. So on data that I've never put. This is called validation. So what we see here in the blue is our loss function going down, which is good, right? We're doing well. And then in orange, you actually see whenever that training step we validate, it also goes down. It's good. But this is not always the case, right? So in some cases, you actually see my loss function is going down, the blue one is doing well, but then my validation is going up. So what it means is that I'm testing a model and actually doing worse. So am I doing something wrong? Right? That's what you ask yourself. And that last thing was called overfitting, which we'll talk about more tomorrow. But essentially, when your network tries to memorize the data, it actually does worse on the real world. And you're better off just going back in time and restarting. So we'll talk about that tomorrow when you're in the coding session. is one of the things that you need to think of when you actually use these neural networks. So then finally, we'll go through just quickly the types of neural networks, because neural networks have been applied to not just images, but in fact to speech, to mathematics, to video, and for each application you need to kind of change it. So people have come up with different neural nets. Most famous one I just showed you is the fully connected neural network. So it's where every neuron is connected to every neuron. Then we have the convolutional neural networks, where essentially stick a window and you look at an image and you slide through this image. So you're not looking at the image as a whole in one go, but you're essentially sliding through it. And this operation is called a convolution in mathematics, hence convolutional neural network. Then we have networks that are recurrent, meaning that it actually is going to get input from itself. So it's going to get output, and that's fed back in to get input, and you form like a closed loop, which is called a recurrent neural net, which is very useful for language because it happens all the time. As I'm speaking, I'm actually taking time for each word, and you need to have that display. And then transformers is just something that came out recently and just destroyed. Like it just performs extremely well on a lot of domains, and it's a lot faster than recurrent neural nets. Essentially, it's like a super power neural network. If you're interested, you can look it up. Transformers have really changed the performance of, like for instance, Siri or anything with voice, even with images. It's really like a recent development. So yeah, here is the fully connected neural net. Everything is connected, right? Then you have some outputs. In this case, some classes that you're trying to put your image into. This is a convolutional neural net. So as I said, you're sliding through the image, right? This is called a convolution. So what you see on the left, the convolution block is your convolutional neural net, and you repeat this in the traditional deep learning, where you repeat this in many layers, and you essentially do the same as what we did before with the fully connected neural net. This is recurrent. So if you imagine the x-axis before in time, we're feeding the same thing that you just got out back in to the network again, and you're kind of repeating it to process data. The reason why you want to do that, maybe you will notice from this picture, is that you actually remember what is happening in previous time step, right? So if I speak to you, you must remember the word that I spoke to, otherwise I don't think we're picking up that much if you have like the memory of a goldfish and you listen to like human speech. It's going to be very tricky, right? So these recurrent neural nets sidestep this issue by essentially feeding its own history. And then just for fancy graphics, this is a transformer. So essentially the key idea is it looks at everything at once. That's the idea. So instead of doing all this fancy stuff I showed you, the transformer looks at everything and does something which essentially is very similar to what we discussed. This network is extremely powerful, but also very hard to run. We will not be running this tomorrow, unfortunately. Tomorrow we'll do a simpler convolutional neural net. So yeah, that's pretty much all the theory. So now I'll just very quickly tell you what people do in practice, prepare for tomorrow. And then I'll show you some demos. Almost there. So hope you are getting more out of this before we actually look at this tomorrow, where we apply machine learning to data essentially. And particularly tomorrow, we'll be using deep learning. But before we do that, usually people are given some data, and then first they explore this data. So it's called exploring data analysis. Then they process the data through some pipeline. They clean up the data, and they perform something called dimensionality reduction, where you have extremely high dimensional data and try to make it smaller. So it's like making a big image smaller, downsizing. And then the third step, which we'll be doing tomorrow, is once we have this cleaned up data, we want to make the model, a machine learning model that actually tries to learn something from this data, and in particular, we'll pick a convolutional neural network. And then we train the model, which we also do tomorrow. You'll see how that goes, where the loss function goes down, and your validation loss hopefully also goes down until you overfit and it starts to go up. And this is where the whole idea of splitting the data into a training set, training, and a validation set for testing comes in. Yeah, the whole concept of overfitting, which you want to avoid. And then the final question I want to leave you with, we've been talking about neural nets because they're popular, but do you actually need them, right? Like, do you actually need a neural network to do all of this? Not always. Neural networks are huge, but you have deep neural nets especially. And they may overfit, they may be slow to train, they may actually predict the wrong thing because they're too complex. At times, sometimes you can do simple linear regression and you can outperform neural nets in some cases, or exactly due to overfitting, as I said. In particular, I just want to remind you that machine learning is not all about deep neural nets. Even though a lot of this was just about deep neural networks, but machine learning actually includes a whole bunch of algorithms, and it takes quite some experience to learn which one to use, which one is best for which task. Even though neural networks are starting to become the go-to algorithm, there are still cases where it's probably better to use something else actually. So yeah, this is what we'll do tomorrow. So essentially, for each neural network, you need to have a set of ingredients that we'll go through before you actually build it and start training it. And this is kind of like a summary. You start with your neural network model, pick a learning rate, which is something that decides how fast you want to go down the hill that I showed you, the loss function. Then you choose the number of iterations, the number of times you want to feed in the data again and again and again until the machine learning model is fed up and it has learned. So you have to pick that as well. And then you have to pick how you want to go down this hill. So the optimization of it. Cool. So next time we'll do PyTorch basically, or official neural nets. I hope today's session was roughly a general introduction to machine learning. You have an idea what machine learning is, what deep learning is, and how they relate, and how this relates to intelligence in general. And this is definitely going to be useful in your life at some point, especially given the current developments in the world. So I hope for anyone who is new to this, that this introduction is a good stepping stone to that. And before we close, let's see if this works. I want to show you some real-world examples of advanced deep learning that has been applied. So this is a video of, you may know it. So this is a car driving itself. So notice that the guy is not touching the wheel of the car with the camera. So this is Tesla, by the way, which has a camera looking at the road. And it can actually drive by itself. Until this point, it almost collided. But before that, it was fine. And essentially, it was using deep neural networks to look at the world through the camera and drive this car by itself, essentially, without you having to drive. I don't know how long this is going to take to complete, but probably in the next 5–10 years, you won't need to learn how to drive anymore because these cars are going to drive themselves. But we'll see if this works. Some people don't think it's ever possible. Some people think it's possible. And yeah, we'll see the outcome sooner or later. And then the last demo. Yeah, so this is from Facebook Reality Labs, which now, as you may know, has been branded into Meta. Essentially, over there, they've been developing something, again, using deep learning, but it's very different. They've been developing a wristband that is able to read your nervous activity, like your nerve cells and your essentially electrical signals that you're sending through. And in particular, because the wrist is like the center of nerves, you have like a very strong signal there, right? And they have made a wristband that's going to read from it and basically allow you to control the virtual world as if you had direct access to it with your nervous system. it's an example of a brain-machine interface, roughly. And you can even type with it without a keyboard, because it just, your brain is sending signals through this, through your arm to the wrist, and this wrist part is picking this up. And then using deep learning, you're trying to reverse engineer what the brain is thinking. And then you can do things like this, where you predict what the person is typing, even though there was no keyboard. I don't want to say this is like reading thoughts, because that's creepy, but it's a bit like reading thoughts. You're converting like the brain activity that has been transmitted to your nervous system. So yeah, that was it. These are the recent developments of deep learning and generally machine learning. And I hope you learned a lot today, or if not, at least you enjoyed it. And yeah. If there are any questions, of course, you can ask them. No questions?